The topic I'll go over in this video today is probably one of the most important topics in statistics. The central limit theorem is based on the distribution of the sample means. Let's do a quick vocabulary check. A sampling distribution is the distribution of all sample means, the means of all samples with all samples having the same size and taken from the same population. So if there was our population, all subjects, then the population mean is abbreviated as mu, and the sample mean is a statistic that describes a sample, and it's abbreviated as X bar. Let me show you an example of sampling distribution. According to CDC, Centers for Disease Control and Prevention, the mean height of American women ages 20 and up is 63.6 inches. By 2015-2016. These data were collected through 1999 to 2016. The mean height, by the way, of the population of women varies slightly over a period of time. If you want to read more details, visit cdc.gov. I'll also put the link to this research in the description of this video. Let's say you want to conduct your own research and choose a simple random sample of, say, 50 women, ages 20 and up. You measure or survey their height and calculate a mean from your sample. Your calculations show that the mean from your sample is slightly different in 63.9 inches. Why is the difference from the population mean? Well, maybe because you play basketball, and maybe in your sample you had a few of your friends who might also play basketball and whose height are slightly higher than the average height of women. Maybe that's why your data might be a little skewed. That's possible. So anyway, those 50 women get so interested in your project that they want to conduct their own research. So each of those 50 women collect a sample, a simple random sample of 50 other women and calculate the mean from each sample. So now you have 50 samples, well, actually 51 with your sample, and you have 51 means. The 51 means might differ slightly. Your mean was 63.9, someone else's 63.2 inches, 62.8 inches, 64.1 inches, for example, and so on. But when you find the mean value of the 51 means, it will be pretty close to the population mean of 63.6 inches, plus or minus tiny sampling error. This error is a standard deviation of the sample means distribution and is found by the formula sigma divided by square root of n. And we'll discuss it in more details as well later. But the larger the size of each sample, the more times the sampling process is repeated. The closer the mean of the sample means is to the actual population mean. Basically, as we increase the number of samples, the value of sample mean approaches the value of the population mean. And the distribution of the sample means approaches the normal distribution. In the example we just reviewed, the population was already normally distributed, so of course, the distribution of sample mean is going to be normal as well. However, according to the central limit theorem, the distribution of the sample means will be always normal or very, very close to normal if either the population has a normal distribution or the sample size is greater than 30. The larger the sample size, the more closer the distribution gets to normal. It's hard to believe, and it is a big statement that we would probably want to verify. So let's do our own experiment. Let's now work with the population that has a uniform distribution. I'm going to use the dice rolling. We know that a die has 6 sides. Each side has an equal probability of 1/6 to appear on the top of the die when I roll it. The population mean is 3.5, which we can find by adding all the sides 1 plus 2 plus 3 plus 4 plus 5 plus 6 and dividing it by 6. 21 divided by 6 is 3.5. So when I roll a die, say 5 times, the average of the top sides should be 3.5. Let's try it. I will roll the dice 5 times and will write which number comes on the top side. And we'll repeat the procedure 34 more times. Just kidding. I'm not going to repeat the procedure 34 times manually. I'm going to use StatCrunch for that. If I do it manually, you will probably fall asleep watching this video. StatCrunch has this amazing feature that allows us to use simulations. It can be found under Applets, Simulation. I'm going to do dice rolling. Dice has 6 sides. Number of dice to roll 1. The average should come to 3.5. Use dynamic seed. Yes, compute. I'm going to roll a die 5 times. So I click on 5 runs and observe a procedure of dice rolling. Here are the sides that will come on top, 1 or 2 or 3 or 4 or 5 or 6. In this case, the average roll or the mean is 2.8. Let's copy it in the StatCrunch data. In the first column, I already wrote the numbers that we got from the first procedure. To copy these numbers in the StatCrunch column, just click Analyze, Data Stored in New Column, OK. And then we can reset and repeat the procedure again. Write it down and repeat again. And we are going to do that 34 times. Or 1, 2, 3, this will be 4, 31 more times. Now that we repeated the procedure 35 times, including one manually, see we end right before column var 36. Therefore, we have 35 sets of data. Now we're going to find the mean of each set. Don't worry, we don't have to do 35 calculations. StatCrunch allows you to simplify this process. Go to Summary Stat, Columns, select all columns, click Mean, Compute. Here are the means of all 35 columns. Now I'm going to copy all these means and insert it in the next column. In column var 37, now we have the means of all our samples. Notice that neither of the mean is equal to 3.5. Interesting. Now let's check for the normality of the distribution of the means, meaning we're going to check whether the distribution of the means is normal, as we predicted. Let's build a histogram. That's one of the ways to check for the normality of the distribution. Histogram. We're going to build a histogram from column var 37, and we want to see the mean on that histogram. Click Compute. Look, the distribution seems to me very close to a normal distribution. If we repeat this experiment infinite amount of times, the distribution of the means will be perfectly bell-shaped, and the mean is equal 3.4857, which can be rounded to 3.5. One of the other ways to assess the normality of the distribution is with quantile plot. Quantile plot is located under Graph, QQplot. Choose column var 37, Compute. The distribution is considered normal if the dots are located close to the line without any specific pattern. If it has a small pattern, it will not be a normal distribution. But if it's scattered close to the straight line, then the distribution is considered normal. I want to show you the examples of the quantile plots of data that don't have normal distribution. For example, the 2015 Major League Soccer players' salaries. Let's build a histogram first. Grab histogram. We're going to choose column 2015 base salary. Compute.
Do you see how skewed to the right this distribution is? Now let's build a quantile plot and see how the quantile plot of the skewed to the right distribution looks like. Again, choose 2015 base salary, compute. Do you see where the dots are located? They're not even close to the straight line. Before we look at how to solve real-life applications using the central limit theorem, let's go over the requirements. The first requirement of the central limit theorem is that the sample is from a population that has a normal distribution, or it's either or the sample size n is greater than 30. Let's read the application. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds, or 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst-case scenario in which the elevator is filled with 27 adult males. Assume that adult males have weights that are normally distributed with the mean of 189 pounds and a standard deviation of 39 pounds. In part A, we need to find the probability that one randomly selected adult male has a weight greater than 148 pounds. First, I want to explain where this 148 pounds came from. When we divide 4,000 by 27, that will be 148 pounds per passenger. The question is, do we need to check the requirements? Well, not yet, because we are dealing with one randomly selected adult male. So we are going to solve this problem regular way, just like we did before. Draw a normal distribution, identify the mean and standard deviation, and identify what area on which side of our x value we are looking for. We're looking for probability of the weight greater than 148 pounds. It's on the right side. Let's use StatCrunch. In the StatCrunch, go to Stat, Calculators, Normal, adjust the mean to 189, standard deviation 39. The direction of probability is to the right of 148. Compute. The probability is 0.8534. The probability that one randomly selected adult male has a weight greater than 148 pounds is 0.8534, or 85.34%. Chance that when we randomly pick one adult male, their weight will be greater than 148 pounds. Now let's look at the next part. Find the probability that a sample of 27 randomly selected adult males has a weight greater than 148 pounds. Now we are dealing with the sample, and the sample size is 27. So we need to make sure that we check for the requirements of the central limit theorem. The first requirement is either population has normal distribution, which it says right here that population is normally distributed. So the first requirement is met. We don't even have to check the second requirement. We only check the second requirement if the population is not normally distributed. Then the sample size should be greater than 30. In this case is less than 30, but it's okay because the population has normal distribution. We just need to make sure to modify some parameters. Mean of the sample will be equal to population mean, which is 189 pounds. But the standard deviation of the sample will be equal to standard deviation of the population divided by square root of n. 39 divided by square root of 27. And we can either manually calculate this value and then enter it in StatCrunch, or let me show you the faster way, how to enter it in the StatCrunch. In the StatCrunch, again, go to Stat, Calculators, Normal. To get to normal distribution calculator, enter the mean 189. Standard deviation is 39 divided by, for the square root, we put SQRT, open parenthesis, 27, close parenthesis. And again, we're looking for the probability of x greater than 148. So leave the distribution to the right, compute. Wow, it's a pretty high probability, 0.99999. So the probability that a randomly selected sample of 27 adult males will have a weight greater than 148 pounds is equal 0.9999, or 99.99% chance that if the elevator is filled with 27 randomly selected adult males, the elevator will be over the capacity. And this is how the distribution of the 27 randomly selected subjects will look like. Now, how do we know when we use regular standard deviation and when we use the converted standard deviation? If we're dealing with just one individual randomly selected subject, then we will not need to modify standard deviation. But if we are dealing with the sample of several subjects, then we first need to check the requirements of the central limit theorem, and second, we will need to modify the standard deviation of the sample.
I hope you found this video helpful. In the next video, we'll look at building the confidence interval for population proportion, confidence interval for population mean, and for population standard deviation. I'll see you soon.